So normally we don't have to worry about the ordering of bits inside a cell's truth table. It's sort of immaterial to our actual designs. But there are a few cases where we actually need to know what order the bits are stored in. And one of those is in the use of crystals. So the idea of a crystal is exactly the same as a crystal in regular electronic circuits. We're using it to generate pulses at a particular rate or pattern. And in a cell matrix, a crystal is really just a cell that's being constantly used to supply a truth table pattern. So here's an example where we have a crystal over here. We place it into C mode from a neighboring cell, which we call the controller. And the bits coming out of the crystal D's truth table are recirculated back in, but are also sent out through one side of the crystal. So it's really just a non-destructive cell read. But the pattern that we put into the truth table for cell X is not based on a particular logic function we want to perform. It's based on a pattern of bits that we want to generate. So if you look at the video that describes bit ordering in the truth table, you'll see how we can, for example, create a truth table whose 8 output columns might contain 1s and then 0s, and then a 1s and 0s, and so on. And since we begin outputting from the last row's data output values moving up, if we store a 1010 in here, the output from this cell will be the bit pattern 1010. And if we repeat this pattern throughout all 8 columns, we'll get a nice steady output stream coming from here, 1010, where this changes value every time the system clock ticks. So this would be our output. The underlying system clock that's responsible for manipulation of cells during C mode would look like this. And remember, every time the system clock ticks, the cell's truth table is interrogated at a different bit position. So here on the tick, we interrogate the 1, the next down tick, we interrogate the 0, and so on. So the highest frequency we can get out of a crystal in this form is 1/2 the clock frequency. In other words, we can generate 64 pulses for every 128 pulses of the system clock. And there's a few ways that we use crystals. One is simply to generate a pulse every 128 clock cycles. That's useful when you want to begin and end a cell configuration operation so that you've loaded exactly the number of bits that correspond to the size of the truth table. So we create a truth table that outputs a 1 in the very last bit position. Remember, that's the 4th C output in the very first row. And after 128 ticks, well, at the beginning of the 128th tick, this output will go high, and at the end of the 128th tick, it will go low. And we can use that to start or stop a configuration operation. But another way we can use this is we can use a frequency doubler. So for example, we can put this through a delay circuit, run it into an exclusive OR, and this will give us a doubling of the clock frequency coming in by XORing a signal with itself, but with a delayed version of itself, so that during this delayed time, the output of the XOR will actually be 1, and then when the delayed version catches up with the direct version, it will drop to a 0. So we can take the output of this, what we would call a 64 out of 128 crystal, and double it to get a signal that pulses every time that the system clock ticks. And it's synchronized with the system clock, so as long as we have that one clock delivered globally throughout the system, we have a way to tap into it and perform operations inside the matrix that are synchronized with this system clock. So that's one way that we can introduce synchronicity into the inherently asynchronous circuits of the cell matrix. We use different kinds of crystals for different operations. This is one of the most common ones is a 64 out of 128. The other one, as I mentioned, is the 1 out of 128, which turns on a single bit each clock cycle. But there are different ways you can do this. Again, this is one of the few places where we need to actually pay attention to the ordering of the bits. And if you load a system with a different truth table bit ordering, your circuits can stop working based on this. So this is the basic idea of a crystal, and it's one of the keys that we use to being able to autonomously configure and read cell configurations inside the matrix.